Thank you. Good afternoon to everybody. Thank you for this very kind invitation, especially to Roberto, who made possible this visit here and to speak with his group. And I am very happy to speak about nucleosynthesis of the first stellar generation. Let me begin by saying a few words about the first stars. Actually, why are we interested into this first generation of stars? There are many reasons. Very rapidly, we can say we want to understand whether these stars could help or could have contributed in reionizing the universe. Of course, they shaped the early chemical enrichment in galaxies. We want to know whether we can recognize whether a starburst is dominated by population-free stars to have some kind of spectral signature. We want to be able to predict the frequency of different transient events. It can go from black hole merging or from long gamma ray burst or short gamma ray burst. We can wonder what is the difference if a star is formed today and between a star that is formed a long time ago when the metallicity was very different. Of course, what makes a big difference is, of course, the initial composition. The first stars were made from primordial material that went through the Big Bang nucleosynthesis. And this has impact on different topics. It has an impact on the way typically the first phase of the evolution will occur. You know that massive stars in the present day will begin to burn hydrogen by the CNO process. But if you take a massive stars, 20 solar mass stars to give you an idea, if it has no metal at the beginning, it has no CNO elements, and so it will begin to transform hydrogen into helium by the pp chain. But the pp chain are not efficient enough for sustaining the loss of energy at the surface. As you know, the luminosity of a star is given by the hydrostatic structure, not by the nuclear reactions. So this luminosity cannot be sustained by the pp chain, and for that reason, stars has to tap another energy reservoir, which is the gravitational reservoir. The star will contract until the point where the temperature is high enough for triggering a little bit of helium burning. And this helium burning will produce a little bit of carbon. When I say a little bit, it's of the order of 10 minus 10 in mass fraction, in order to switch on a small CNO cycle, if you want. And this small CNO cycle will allow the star to continue to burn hydrogen into helium. But from this line of reasoning, you can imagine, or you can, let us say, deduce that the temperature of burning in this very metal poor star, in population-free stars, is much higher than in present-day stars, because the star had to contract to really reach central temperature very nearby from helium burning. And this has important consequences for the follow-up of this story. Of course, you have other differences. You have difference about the mass loss by line-driven winds. In the massive stars today, you have some lines which will absorb part of the radiation and will allow some of the energy in the radiation to be transformed into a mechanical kinetic energy of the winds. But if you remove heavy elements which have many absorbing line, you will decrease a lot the winds, the mass loss by the line-driven stellar winds. So a population-free stars will not lose mass by this process, at least. Another difference is also the mixing induced by rotation, but this I will come back in a while, so I will not say much at the moment. You have also other possibility of differences. We don't know what has been the role of multiplicity of closed binary in population-free stars. We don't know the role possible of magnetic fields also. So these are more question marks. We can say that probably the first stars enrich locally some part of the universe, because you need sometimes for ejecta of all stars to be mixed together and to produce a kind of homogeneous interstellar medium from the point of view of the chemical composition. So at the beginning, you can imagine that you have some spots which are enriched by a few stars, another spot by another type of stars, and you have a scatter of chemical composition. So the degree of mixing is probably less when we go farther and farther away in the time history. You have also that the initial mass function could be different. At low metallicity, you are favoring more massive star formation. This is related to the fact that you have no dust, and the dust is a very efficient cooling mechanism that can evacuate the energy produced when you contract a sphere of gas. And allows us, if you evacuate this energy, you can allow the contraction to be pursued and the fragmentation to be pursued, which is not the case at low metallicity, or less the case at low metallicity. You can also imagine differences which are due to more speculative, I would say, ideas, as the fact that the fundamental constant of physics could be different, which may have an impact on the way the stars are evolving. And also, the first stars are born in mini halo of dark matters, and depending on the characteristic of a dark matter, for instance, if we have a Majorana particle that can, by interacting with themselves, disintegrate, it can produce a source of energy in the first stars. But I will not speak about these topics, just to make a kind of landscape. I would like to focus on the physics here of rotation of stars, the spin-up of stars. Actually, not the spin of stars. Rotation can have an impact on many aspects of the physics of stars. Of course, when a star is rotating fast, it can make its hydrostatic equilibrium shape different. It can make it oblate. It can also impact on the mass loss. Typically, if you make a star oblate and fast rotating, the pole will be brighter and hotter than the equator, and this can drive some jets, or let us say some anisotropic stellar winds, if there is stellar winds. You can also change a lot the mixing. Actually, you know, rotation is a bit like when we use a spoon to mix the sugar at the bottom of a cup of tea. It is exactly the same to some extent. In massive stars, you have some, for instance, helium, which is produced in the core, and this helium remains in the convective core if nothing happened, because the radiative layers above are stable. Stable, it means that if you displace a little bit of parcel of matter in this radiative envelope, it will come back to its equilibrium position. But if you have instabilities triggered by rotation, and I will tell you more in a while which stabilities we are considering in the models, then you can mix, you can transport elements also in the radiative zone. And you can, for instance, mix helium produced in the core in the envelope, lower the opacity in the envelope and make the star brighter, for instance. But there are many other consequences. You can also trigger a dynamo in the radiative zone, which will amplify magnetic field, and also this has impact on the angular momentum transport. Of course, a difficulty is that at least rotation is a 2D process, and we have, in order to be able to model very different models of different masses, metallicities, initial rotation, maybe with a companion or not, we need 1D stellar evolution code. So how we go from 2D to 1D, and when I say 2D is really the least that we can imagine, because 2D is even not enough. Convection, many turbulent processes are in 3D. The problem is that 3D models are extremely computing expensive, and it's not possible at the moment to compute really evolution with 3D models. So we have to inform a 1D stellar code on how to treat the effect of rotation. Actually, the idea comes back from a paper by Jean-Paul Tsai in '92, where he actually deduced some equation for the transport of the angular momentum and for the transport of the chemical species, starting from one a priori hypothesis. Actually, he said that you can have differential rotation both along the vertical direction, because the core is contracting during the main sequence, so it will spin up, while the envelope is slightly expanding, so it will spin down, and you have a gradient between the two, and this gradient will make a shear instability. The shear instability comes from the fact that, to some extent, differentially rotating layers have more energy, more kinetic energy per unit mass than the same layers rotating at an average velocity. And so you have an excess of energy in the differentially rotating layers that can be used to mix the two layers. This is what we call the excess energy in the shear. But you can have also differential rotation along an isobar horizontally, you know, and these instabilities horizontally can be very rapidly washed out by a strong horizontal turbulence, which is due to the fact that, contrary to what happens in the vertical direction, the turbulence, in order to mix the matter, has not to struggle, if I can say that, against stable temperature and density gradient. So it can really wash out any differential rotation along an isobar. And CERN assumed that the stars are rotating in a cellular way. Cellular means that each shell is rotating with one specific value of omega that can, of course, vary from the surface to the center, but with the same value everywhere as a function of the latitude or the colatitude. And from that, he deduced the two equations that I show you here. One, the first one is the equation describing the mixing of the chemical species due to rotation. And you have two diffusive coefficients, one which describes the effect of the shear instability, and the other one which describes a concomitant effect of two instability. One is meridional currents, and the other one is a strong horizontal turbulence. And you have in the second equation, the equation describing the transport of the angular momentum. And here you have also two parts. One part which is advective, which accounts for the transport by the meridional current, and another one which is diffusive, which accounts for the part due to the shear turbulence. We can wonder why there is a difference between the transport of the chemical species and the angular momentum. Why not the same equation for both? The main reason is that if you imagine a small piece of matter in the star and you move it up along a radial direction, actually the quantity of angular momentum that you transport depends on the distance to the rotational axis, which is not the case for the chemical species. So this change in the physics between angular momentum and chemical species makes the change in the equation. Of course, we could spend the whole rest of the seminar into discussing different types of rotation. Today, I will focus on one type of rotating models. Maybe what you have to be to keep here as a message is that when you use rotating models for whatever use, for the yields, for the population synthesis, actually this under, or let us say, behind this term of rotating models, you have many different physics. You know, you have models which account for the two hydrodynamical instabilities, like meridional current and shear instabilities. You have models which account for magnetic instabilities. And even if you have models which both account for the same physics, they can give very different results depending on the way the numeric is treated. But I have no time to illustrate this. But today, I will focus just on models accounting for shear and meridional currents. I will not speak about magnetic field induced by rotation, even if it's very interesting topics. Now let us come back to the first stellar generation. We can wonder whether we have some indication that stars are rotating fast at low metallicity. We have not, of course. I have just a few very indirect indications. There is a work, typically the one by Athena Stasi and in the group of Volker Brom, who have, through smooth particle hydrodynamic, tried to modelize the formation of the first stars. And one of the conclusions is that in absence of magnetic fields, the star would rotate very rapidly when they are born, very near what we call the critical velocity being defined as the velocity at the equator at which the centrifugal acceleration balances the gravity. Another indication, which is a bit, let us say, of course, controversial, but it's the BE-type stars. BE-type stars are stars in the present-day universe that lose mass through an equatorial disk. And the idea is that this process is driven by their fast rotation, at least in part. in the sense that all B stars are supposed to rotate at least at minimum at 70% the critical velocity. And what is interesting is that the fraction, the number of B stars, or fast rotators, if you want, with respect to the total number of B stars, seems to increase when we go toward low metallicity. Of course, here the low metallicity, the lowest one is the one of the SMC, the small magic cloud. So we cannot go very far away in the low metallicity range, but it may indicate that for whatever reason, is it due to formation, is it due to the spin-up, due to tides, for instance, in a closed binary system, we have a larger fraction of fast rotating stars at low metallicity. So it's not completely unreasonable to say that maybe if rotation is important, it can be very important for the low metallicity or propulsion-free stars. The second point is that from a physical point of view, we expect that the mixing in these very metal-poor stars or propulsion-free stars is more efficient. What does it mean? First, it means that typically if I compare, you have these plots here where I compare kind of evolutionary tracks. It's for, I guess, I don't remember, I think it's for 9 solar mass stars. And you have the effective temperature in the horizontal axis, like in the normal Hess-Pungosel diagram. And you have on the vertical axis the evolution of the nitrogen over C ratio at the surface of the star. So we know that in the core, nitrogen is built at the expense of carbon due to the cyano process. If there is no mixing, we will never see at the surface these results. But if you have some mixing, the surface will be enriched and depleted if you also enrich in nitrogen and deplete in carbon. And you have the evolution of the surface abundances as a function of time of different tracks. The red one corresponds to the solar metallicity one, or let us say the metallicity of 0.020 because it's no longer the metallicity of the sun. The green one corresponds to a factor 5 less metals, and the blue one corresponds to 10 minus 6 or 5, so 5 in mass fraction. And you can see that you have more and more nitrogen enrichment for the same initial mass, the same initial rotation on the SAMs when you decrease the metallicity. Why it is the case? The case, it is because, one of the reasons is because the star is more compact, because of what I explained before. The star has to contract more in order to, even if there is cyano element, it has to contract more in order to produce the energy required to compensate for the loss at the surface. So the star is more compact, and the time scale of the mixing is proportional to the square of the extension of the radiative zone divided by the shear diffusion coefficient. If the shear diffusion coefficient is more or less the same, which is the case, it's even higher in low metallicity star. Since the extension is shortened, you decrease the time scale of the mixing. And actually, I will not comment this plot, but it is an observation of nitrogen enrichment at the surface of different stars at different metallicities. Actually, we can say that observation goes in the same direction. It seems that the B-type stars are more nitrogen enriched when they are belonging to the SMC than when they are belonging to the solar neighborhood. But these are mixing between a hydrogen burning core and the envelope. But you can have mixing between in later phases of the evolution. Typically, you know, at the end of the main sequence, the core, which has been transformed into helium, contracts, so it will rotate faster, and the envelope will a little bit continue to expand. So it will make a strong shear, a strong differential rotation between the helium core and the hydrogen burning shell. And this shear can trigger mixing that can bring some elements produced by the helium core into the hydrogen burning shell. And among the elements which are produced in the helium core, we have carbon and oxygen. And this carbon and oxygen, which can be have very high abundances, can migrate into the hydrogen burning shell and transform into nitrogen. I have here a small diagram showing this kind of back and forth mixing. The first one on your left shows a region where you have helium burning product with carbon and oxygen at a high level. This carbon and oxygen can migrate by rotational mixing into the hydrogen burning region where it is transformed into nitrogen-14 and into carbon-13. So it makes a lot of nitrogen and carbon. Then, in the second step, you have this high nitrogen, and carbon-13 can migrate backwards into the helium-burning core. And the nitrogen can produce neon-22, and magnesium-26. Carbon-13 will be destroyed. And this neon and magnesium, at their turn, can migrate back into the hydrogen-burning zone and produce aluminum-26, sodium-23. So this back and forth can open a relatively rich channel of nucleosynthesis that would be impossible if there was no mixing between the helium and the hydrogen-burning region. Maybe just to tell you a small difference that people who are doing chemical evolution are sometimes using is the difference between primary and secondary element. Actually, we call a primary element an element that can be produced in a propulsion-free stars. You start from nothing, there is no metals, and you can produce a quantity of that element which is significant. In that case, you know, typically the nitrogen, normally in a propulsion-free stars, it cannot be produced during the hydrogen burning, because during the hydrogen burning there is no CNO element. There was a little bit of carbon produced, as I explained before, but this is 10 minus 10. So even if you transform all this carbon into nitrogen, it remains 10 minus 10 in mass fraction of nitrogen. So there is no possibility to produce nitrogen at a high level from propulsion-free stars from hydrogen burning. In order to produce a lot more, you need to wait for the next step where you produce a lot of carbon and oxygen in the core. You allow, by some process, these elements to migrate into the hydrogen burning shell, and you boost, of course, the production of nitrogen. In that case, if nitrogen is produced by a primary channel, you expect to have a N over O as a function of O over H, which evolve as a function of increasing metallicity as a flat, as a plateau, because nitrogen will evolve in lockstep with another primary element, which is oxygen. Instead, later on, it may be that nitrogen will be produced mainly by secondary process. In that case, you will produce only the amount from the initially existing carbon and oxygen in the core. It will produce during the hydrogen burning phase, and the total amount of nitrogen that you can produce is at most equal to the initial CNO content, because as you know, the CNO burning path will not change the sum of the CNO elements. And in a chemical evolution models, you will have an increase, which is not a plateau like in the first case. Okay, what time is it now? Oh yes, okay, I have to speed it a bit. So maybe I will skip this one because it's just to mention that CNO, we are sure that it is produced in stars because we can see stars which have removed their hydrogen-rich envelope, and we can see the core. We can see the abundances which are produced by the CNO cycle. But this is a bit long to explain, so I will skip because otherwise I will miss. So these two facts, the fact that mixing seems to be favored for a given rotation at low metallicity, and the second point that there are some indications that maybe the number of fast rotators becomes higher and higher when we go toward low metallicity, imply that maybe we can expect some processes, nucleosynthesis, which is governed by rotation at low metallicity. I just show you here two chemical structure of 60 solar mass stars, one on your left coming from a model rotating very fast, 70% the critical velocity on the ZAPs, and on your right, the same model, exactly the same, but with no rotation. And you can see that on your right, you have that in heavy green, you have the abundances of nitrogen inside the model. Actually, the x-axis is the Lagrangian mass inside the model. So 0 will be the center, and you can see how it varies inside the star. And what is shown here is a part of the star which is at the frontier between the helium core and the hydrogen burning shell. And you can see that in the non-rotating model, the nitrogen level is around 10 minus 5. And the initial metallicity of that model is around 10 minus 5. And it's not by luck. It's because, you know, CNO elements are representing maybe 3/4 of the whole metallicity. And if you have a secondary production, which is the case here in these non-rotating models, the highest level of nitrogen that you can reach is the initial CNO contents, 10 minus 5. Instead, on your right, you have the case of the rotating models, and you can see that you go from 10 minus 5 to 10 minus 2. Yes, 2. So it's very impressive. It's 3 orders of magnitude increase. Okay, we have computed a lot of models with different mass, and what is interesting that maybe this is the only thing that I can retain from this plot. You have at the bottom the difference between the non-rotating and the rotating one at low metallicity as a function of the mass. And above, the blue tracks are for solar metallicity. For solar metallicity, you don't produce that. You don't produce this mixing between the core helium and the hydrogen burning phase and the hydrogen burning shell. Why? Because in a high metallicity stars, the distance between the border of the helium core and the hydrogen shell is much greater. And even if you have some mixing, it's very little impact. And why in low metallicity the two are so near? It's because the stars are more compact, but also because the temperature of hydrogen burning is very near from the one of helium burning for the reason I was explaining at the very beginning of this talk. So you have a system that implies a kind of primary nitrogen production, but focused only for the low metallicity. It will not work for the high metallicity. Of course, to have yields of massive stars is not the only, I would say, conditions to look what happens for the evolution of a galaxy. You need a model. And actually, here I just show a model that Cristina Ciappini, who was working at the time in Geneva, was giving to me. It's a model for the halo of a galaxy. And it's a model that is calibrated in order to reproduce the metallicity distribution of stars in the halo. And actually, what is interesting in this diagram, you can see how the metallicity in these chemical evolution models increase with time. So on the upper diagram, and this is the one I would like to look now, discuss, you have the evolution of Fe over h as a function of time. And you can see that after 20 million years, in this model, of course, it's model dependent, but in this model, you will reach a Fe over h of -4. And it means that it is reached in 20 million years. Only stars more massive than 10 solar masses could have contributed to this enrichment because the others have not ended their evolution. After 45 million years, you reach Fe over h -3, and only stars more massive than 7 solar masses could have contributed. And if I look at the most distant galaxies, if it is still of actuality, I don't know, which have been observed with the James Webb, it was at the time 13.2. It would correspond to a Fe over h of -2. And I learned in a meeting where we were both together in Bern, in EC, that to date, no oxygen abundances below a few % of the solar value has been measured with James Webb Space Telescope. Of course, it can be by luck, but maybe we can say that what we see with the James Webb are starburst regions, which have, I would say, a chemical evolution a little bit similar to this starburst region here for the halo. And it's not so surprising that there is this flaw of a few % because the metallicity is increasing extremely fast. Let us coming back to nitrogen. If we look at the stars in the halo of galaxies, we can wonder whether it will have a shape from a secondary production. Here, what we see are observations at relatively high metallicity. Actually, I will show the O over H horizontal axis in a few minutes, but here it's just indicating time. And if we have a secondary production, we will have such a behavior if we look at more and more or less and less metal-rich stars. But actually what is observed, it was the observation at that time, but it has not much changed. We see a kind of plateau N over O. So we can say that from that, it gives some confidence that you need some primary nitrogen production. So we can wonder, if we use rotating models, we put them in the chemical evolution models, do we obtain this plateau? And we first did the exercise and we obtained this kind of line. So we were happy to have a plateau, but much lower than what is observed. But in that model, we use initial rotation rate similar to the one of the solar metallicity, so the same initial rotation. But we could have chosen a more, I would say for me, reasonable hypothesis, saying that it's not the rotation, surface rotation which should be similar between solar metallicity and low metal pore stars. Maybe it's more the angular momentum content initially in the stars. And the angular momentum content, because the star is more compact and because its moment of inertia is smaller, for a given angular momentum content, because the moment of inertia is smaller, the rotation rate is much higher. So I have just given some numbers here for a 20 solar mass stars. You can see that if we have a 20 solar mass stars with an initial rotation of 300 kilometers per second, it has an angular momentum of about 0.36 in these units here. If we take the same 20 solar mass stars at low metallicity, with the same initial rotation, it has a much lower angular momentum, 0.18. If we want to have the same angular momentum than its solar metallicity sibling, you need a 600 rotation at the surface. So we use this initial rotation. The first line here is obtained by using the smaller angular momentum models. And when we use the higher angular momentum model, higher with respect to the small one, but the same as the solar metallicity one, we have a much better fitting of the observations. We can look, of course, on the impact of the CO fraction, which is indicated below. I am not sure what time is it. I think 10 minutes still. So I will go fast, maybe on that point. What I showed is a kind of, let us say, support of the idea that nitrogen, primary nitrogen production is needed at low metallicity, and that maybe, we have to be cautious, rotation could be the cause of this primary nitrogen production. But I would like just to spend, to tell you that we have also a similar argument coming from the carbon-enhanced metal pore stars. Actually, I would say that carbon-enhanced metal pore stars, metal pore is not a good name, because these stars are very rich sometimes in carbon, in nitrogen, in oxygen. And as you know, in astronomy, we call them metals. So these stars are not metal pores. We should have named their carbon-enhanced iron pore star, because indeed, their Fe average is very, very small. To give you an example, you see, if we look at a plot like this one, where you have the metallicity in the x-axis, Fe average, and you can see that below -4, you have a few points which are very high in carbon. Actually, the record is obtained by the Keller star. Keller star has a carbon over iron, which is nearly 5, and which have a Fe average less than -7. We could say it's a population-free star. It's nearly deprived of any iron, but it's not, because it's very rich in carbon. Okay, so these are the carbon-enhanced metal pore stars, and there are different categories. There are the CMP NO, S, R, RS, and so on. I will not go into this point. But my point is that the most iron pore stars are probably, or could be explained, by being formed from the ejecta or a very few, let us say, extremely metal pore or even population-free stars. So we can imagine kind of mother star, if you want, which has polluted some part of the universe, from which some small mass stars that are long-living, that we can still see today, from which some small mass stars have been born. And so the surface composition of these stars, at least during the main sequence, is not supposed to have been modified. At least there is no way on the main sequence to enrich the surface in carbon, for instance. So it's why during the main sequence we can see that what we observe at the surface is reflecting the chemical composition of the cloud from which a star formed. I have indicated here some range of value observed at the surface of CMP NO stars. The gray bar gives the range for stars which are believed to be on the main sequence. And the red bar corresponds to stars on the red giant branch. And you can see you can have a lot of carbon, nitrogen, and oxygen. And if we look at the models, this is a model, the blue line is for, let us say, if we look at the ejecta of a 60 solar mass stars, and we mix this ejecta with 100 times more interstellar medium. If we do that, you obtain the blue line, and you can see the blue continuous line, and if you don't rotate, you obtain the blue dotted line, or yes, dotted line. And you can see that one of the big differences is about nitrogen. The nitrogen is very low in the non-rotating stars because there is no this mixing between hydrogen and helium, burning zones. You can do the same with the lower mass stars, 7 solar mass stars. 7 solar mass stars is also the case. If you are not rotating, you never produce the nitrogen in the range which is observed. So the point is that these CMP stars give also a hint that some primary nitrogen production occurs in very metal poor stars. So I will finish, and this is why I wanted to revive at this point, especially because we discussed with Roberto and his group this morning, is the question whether the very high N/O observed in high redshift galaxies could be linked to such processes. So I will like to show this wonderful diagram by G and in the group of Roberto. And actually, you can see the black dots which represent H2 region of local galaxies. And you have the colored point represent galaxies. Most of them, except Macarian, are high redshift galaxies. To connect with what I was telling you before, if I look at the plateau I was mentioning before, we will be at that level, you know, the blue line. So we are much below what is observed in these galaxies. But of course, we have to be aware of the fact that this line, this blue line, is not only affected by the yields that we are using, but also by the chemical evolution models. Typically, how you mix the ejecta, how you combine the different generations of stars, and so on and so on. The question is, how can we explain this very high value? Can we explain this high value typically with using maybe the same yields as the one that is used for the blue line, but with a more simplistic models, with maybe, let us say, instead of having a sophisticated model for this halo with inflow, outflow, and so on, we have a much simpler model. So this is what actually my students recently did. They were using yields of models of fast-rotating propulsion-free stars that were recently computed by Sophie Tsiatsu, and they tried to see whether, with a very simple model, they can explain the N/O so high. Actually, what they did, they suppose that there is a starburst where stars of mass between 9 and 120 solar masses are born. They look at the impact of IMF. They look also at different metallicity. They look whether the stars are rotating or not. Then, of course, at least for the propulsion-free stars, you have no winds, so you have to lose some mass at a given point. And here, they choose to say, okay, these stars will explode in a supernova event at a given point. They will lose some mass. And here, they have to choose what portion of the star is lost. And they choose two possibilities, everything above the carbon-oxygen core, or to use a more deeper mass cut, which is more inside the star and given by some recipe. Here is the one provided by Patton and Sugbo based on 1D stellar explosion models. And then when you have this ejecta, you have to mix with some, to dilute with some mass around. Because what you are looking at in the interstellar medium is probably not pure ejecta of one or a few stars. You are looking at ejecta of many different types of stars, which are mixed with interstellar medium. And so the results are here. Here it's a bit complex, so I will just look at the upper left diagram, N/O as a function of O over H. And maybe I will show the big one, the green line, which is a model where you have taken an initial metallicity of 10 - 5. Here they have also looked at population 3, but it's 10 minus 5, where rotation had already a big impact. And actually, these 10 over 5 models, you will mix the ejecta with the initial composition at this low metallicity. But the quantity of nitrogen and oxygen is so high produced by these stars that when you mix with very low content of nitrogen and oxygen of interstellar medium, it will nearly not change N over O. It's why it's nearly, let us say, when you dilute the mass going from the right or from the left for you, no, from the right, sorry, where you have the highest over H to the left. More you dilute, more you have low oxygen content. Because, of course, you add matter, which is very poor in oxygen because it's a 10 minus 5 initial metallicity. So this green line in the upper diagram show you the N over O that you obtain by taking the ejecta of all these populations, different mass stars. You mix with, let us say, 1, 10, 100, 1,000, 10,000 times interstellar medium, and you make this horizontal line. So only O over H is affected by the dilution. The N over O is nearly not affected. It's just a little bit bending at the end when you have a very high dilution. What I can say is that, okay, you can at least obtain a relatively high value of N over O, and you get value of C over O, which are, let us say, somewhere, not in the middle of the point, but they are somewhere. It's a very simple model, let us say. What I can say is that there is a possibility that production by rotation of primary nitrogen, primary carbon, and oxygen could indeed help in explaining the high N over O. But of course, for me, it's much more complicated than this. To some extent, we can say that there is some hopes to explain this range of value. But as you see, there is still upper range. So the question is whether we have a possibility to explain this higher value. And this is actually a typically similar model as before, but where we looked at much more massive stars. Why? Actually, we considered a hydrodynamical simulation for the formation of stars in mini halo of dark matter that was obtained by John Regan with John Wise. And actually, they are following the zinc particle, which are growing in mass. And actually, they showed that the accretion on this zinc is varying with time because these particles are moving into this mini halo, sometimes exploring very dense region in the interstellar medium, sometimes very low region, and so the accretion rate is changing. And so they have given us their accretion rate that vary as a function of time, and we have used them as an input to compute the formation of massive star by accretion using this accretion rate coming from this hydrodynamical simulation. And then we have evolved those stars, which can reach masses up to 10,000 solar masses, and we have looked how they can enrich their surrounding by assuming that part of their mass will be lost at the end of the evolution. So I just show you this, typically on your left here, you have the variation as a function of time of the accretion rate. And you have on your right a Kippenheim diagram. You know we love a lot Kippenheim diagram in stellar evolution. It's a diagram where we can see the evolution of the total mass of the star. It's a total radius here of the star. And the dark zone correspond to convective zones. Actually, these models reach very high value, as I said, few thousand solar masses. And these stars are sustained mainly by radiation pressure. You know the beta P gas over P, the P total, is very small. It can be a few percent only. So it's nearly photon stars, if you want. There is a little bit of course, gas, but it's mostly radiation. And this favors a lot convection. And you can see that at a given point, even if there is no rotation, the hydrogen burning shell, that is where the yellow arrow point is dredging, is going down where helium burning products are. And this can produce exactly the same mechanism as rotation. It can produce a lot of nitrogen. And so you can see here the profile of the different abundances in these 9,000 solar mass stars at the end of the evolution. So you can say now you lose maybe 10%, maybe 40%, maybe you lose everything above the CO core, and you can at least explore what could be the consequences. Of course, it's far from being a very, I would say, a robust model. What I show here are two things. On one, you have the gray histogram, which corresponds to a kind of IMF. It's a number of stars of different masses which are produced in the simulation by John Regan. So we didn't here assume an IMF. We took the number of stars formed by the hydrodynamic simulation. And you have in colored, you have the quantity of a given element ejected. Here it's oxygen in magenta and nitrogen in red, depending what amount of mass you are losing at the end. And this amount of mass is completely free. We don't know. We don't know. If you do that, and if you do the same trick as before, you can make comparisons with the observation. And here I have added also the point of the galaxy that you have studied, GS 3073, is it right? So this is a red point. And you have lines which are solid, are mixing the ejecta of all the masses, accounting for the IMF coming from the simulation. And the dotted line corresponds to the ejecta of one of these very massive stars. Here we feel that it would be possible to think that one massive star that can eject many thousand solar masses can indeed produce an effect on the chemical enrichment of the surrounding. So we see that it's not possible accounting for the all stars together to account for the very high N/ρ ratio observed in GS 2073, but it might be possible if we consider stars of 6,000 solar mass stars, for instance. So but of course, it's just one ratio. Of course, if we look at the CO ratio, we are a little bit too low with respect to what is observed. But anyway, for the N/ρ, we can say that the very massive stars, up to 10,000, could possibly reach this high value. Okay, I think that I will stop here. I will just mention that we are computing also still much more massive stars by accretion. Actually, here you have a plot obtained by Devesh Nandan, who has just finished his PhD, where we can see the most massive stars which is reached by different accretion rate. What is interesting is that up to 100,000 solar masses, the star can live and can go beyond hydrogen burning. It can produce helium burning core and so on. But above 100,000 solar masses, the instability will occur during the hydrogen burning phase. Actually, at 1 million solar masses, it occurs even before any hydrogen burning occurs. So in order to have at least an interesting nucleosynthesis beyond hydrogen burning, you need to have stars with a mass below 100,000 solar masses. And you have here the Sprung-Russell diagram where I show the evolution of those stars. We can reach luminosity up to 10 to the 10.5 solar luminosity. And they are red because they are accreting so much mass that it inflates, it gives a lot of entropy to the star, which makes them to be very inflated. So my conclusion now, maybe, of course, it's very speculative what I have told you. I tried to at least give some arguments supporting, but I must say that we are very far away of having understood what happened. But what we maybe have to keep in mind is that all these processes, all these abundances that we see, needs to understand stellar processes, like the one of rotation, of mass loss, typically, because even at low metallicity, you can have some process where the star can lose mass. The mixing process is, of course, complex, because rotation is by far not very well understood, and the efficiency of rotation is not very well understood. And you need an ejection process. If you keep all this stuff in the star, it will not enrich the interstellar medium. So already there, from the stellar point of view, you have at least 3 points which are relatively complex to resolve. But in addition to that, you have to know what happened to this ejecta, how they mix with the interstellar medium. And this is another complexity. Okay, I thank you for your attention, and I hope that it was useful for you to hear this story.